Good morning. Let me test my testing.
Your speakers are working now.
There, now it's working. Okay, let's see who we got here so far. Okay, good morning. So, okay, today we're going to start chapter 4. Chapter 4, I'm going to say, is probably the most longest in concepts of all the chapters we're going to cover, because chapter 4 deals with polynomials. Polynomials. What is a polynomial? Okay, so far we've discussed monomials. Monomial is an equation that has one term. A binomial equation has two terms, mono, bi. A trinomial is an equation with three terms, and so on and so forth. A fourth has four terms is quadrinomial. So a polynomial has many terms. So in this chapter, we're no longer limited to how many terms we have in our equation. In the past, we had equations like y equals 2x. Binomial, 3x plus 2 equals 0. Y equals x squared plus 6x plus 5. We have three terms, two terms. So now, but in polynomials, we're not limited to anything. So a polynomial is an equation with two or more terms. Polynomial looks like this. Where a's are the coefficients, n is the degree, is the exponent. That's a sub 1 x1 plus a sub 0. So it could be as long, or again, n is the degree of the polynomial. It's the highest or the largest exponent. An xn, which it's the part, this is the term of the polynomial that has the largest exponent. That's called the leading term. And the number in front of the x, the coefficient, is called the leading coefficient. So again, polynomial, whenever you have an equation, always rewrite your equation so that the exponents are decreasing in size. So for example, the exponents go 6, 5, 4, 3, 2, 1, and then the constant number. So always put them so it's decreasing order. All right. So let's see what else. Now, what does the leading coefficient tells us? This is a direction and width of the graph. The exponent, the degree, tells us the shape of the graph. It tells us the maximum number of X-intercepts we'll have. And n minus 1 is that? And whatever the exponent is, minus 1 tells us the number of vertices. So just by looking at an equation, you could tell a lot by it without doing anything, just by looking at it. So the leading coefficient tells us the direction and the width. And the degree tells us the shape of the graph. I'm going to give some examples in a second. And it tells us the maximum number of X-intercepts. And n minus 1 tells us the number of vertices. So we're always going to have one less vertices than we have X-intercepts. Yeah, this became evident when we have a parabola. We have 2 X-intercepts and only 1 vertex. So it's always one less number of vertices than X-intercepts. All right. So let's look at what this means. Let's pretend our function was x to the, it's a third equation. It's a cubic equation. And I'm going to exaggerate the graphs, but this is what it's going to look like. Because, I mean, the equation will have other stuff behind it, but it's the largest exponent that tells us what the shape of the graph is going to look like. Since the leading coefficient is positive, it's an increasing graph, which means as we go to the right, the graph will eventually always go up. Let's say we had -4. Since that's +1, then since we have a 4, that means our graph will be 4 times skinnier than that. And since it's negative, it's going to go down. So again, when we talked about in transformations in chapter 2, it's the same thing applies here. If it's an integer, if a is greater than 0, if the absolute value of a is 0, then we have a vertical stretch. I mean, our graph gets taller. If our absolute value of a is between 0 and 1. Oh, I'm sorry. I should say if it's greater than 1, not 0. If it's between 0 and 1, that's a vertical shrink. Our graph gets shorter. So the same thing applies as we did transformations earlier. So back up here, we have a cubic equation. So this degree tells us we'll have at most 3 x-intercepts. 3 minus 1 is 2. That's the number of vertices. We have 1 there and 1 there. Okay. Let's look at x to the 4th. It looks like that. Remember, even degrees the ends point the same direction. We call that end behavior. So if the degree is even, then we know both ends point the same direction. So if we had negative coefficient, then our graph would look down. We have 1, 2, 3, 4 x-intercepts at most, and 4 minus 1 equals 3 number of vertices. And so on and so forth. If we have 5, if x is 5, then we'll have 5, we have at most 5 x-intercepts. Let me show you what I mean. Why at most n number of x-intercepts. But when we talked about the quadratic equation, we said that there were at most 2 x-intercepts. We have 1, 2. Or we can have only 1. Or we have no x-intercepts. So even degree equations can have any number of x-intercepts between 0, and n. With even degrees, you can have no x-intercepts, or you can have 2. Even degrees can have any number of x-intercepts between 0 x-intercepts and n x-intercepts. So let's look at x to the 4th. We can have 4 x-intercepts. We can have 3 x-intercepts. We can have 2 x-intercepts. We can have 1 x-intercept, or we can have no x-intercepts. So 4, 3, 2, 1, 0. Okay, so again, if you have an even degree, then you can have anywhere from that number all the way down to 0. So it's any one of those. So let's look at if n is odd. Let's start with 1, just x to the 1st. That graph, what's that? You have 1 solution, 1 x-intercept. X cubed. We can have 3 x-intercepts. Remember, x-intercepts equal solutions, or zeros. They're the same location, they're only written differently. X-intercepts are points, zeros are numbers. So x to the 3rd, we can have 3 x-intercepts. We can have only 2 x-intercepts. Or we can only have 1 x-intercept. X to the 5th. One, 2, 3, 4, 5. One, 2, 3, 4. One, 2, 3 solutions. two solutions. Or one solution. And at most n minus 1 vertices. All right, so each of these we had 1, 2, 3, 4. But again, I could, depending on how the equation looks, x to the 5th can look like this. Or like that. It looks like the same as x cubed. But there's no bends in it. It's just by itself. Once you start adding other parts to the equation, that's what gives it its shape. So what do we notice about odd exponents, odd degrees? So for odd degrees, you can have n number of x-intercepts solutions down to 1. You must have at least one x-intercept or solution. Because both ends of the graph point in different directions. One side has to eventually cross the x-intercept, x-axis. All right. So with everything I just showed you, we have what's called the leading term test. Remember, leading term is the term that has the highest exponent. Okay, these are going, the degrees can be even or odd. And the leading coefficient. The leading coefficient can be positive or it can be negative. If the leading coefficient is positive and the degree is even, only thing we know for sure is that the both ends point up. What happens in the middle, we don't know, because if depending on what the degree is. But we know both ends point up. If A is negative and there's even degree, then the only thing we know for sure is both ends point down. If A is positive, if the leading coefficient is positive and the exponent is odd, then all we know for sure is both ends point opposite directions, with the right side going up, left side going down. And if the leading coefficient is negative and it's an odd degree, the only thing we know for sure is that both ends point opposite direction. The left side points up, the right side points down. All right, so just by looking at the leading term, we can tell what the basic shape of the graph is going to be. And the size of A determines whether it's going to be vertical stretch, shrink, or it's look at the rest of the stuff, it's be horizontal. All right. I'll go to the next page. Polynomials versus non-polynomial functions or graphs. Examples. Looking at your library of functions, this is quadratic, this is cubic, this is x squared, this is x cubed, this is cube root of x. This is the log of x. This is an exponential equation. Non-polynomial equations. Here are the graphs of non-polynomial equations. This is the absolute value function. This is the square root function. We'll talk about this a little later. This is the 1 over x, and this is 1 over x squared. It's the Atari function. The difference is continuity. A continuous function has a domain from negative infinity to positive infinity. No breaks. Like, notice all these curves. If I start at one end of the graph, I go to the other end without ever lifting my pen or making sharp changes. The absolute value is not, because I go down, and obviously it's straight up. There's no transition there. The square root function, you can't have negatives, so it's not continuous before 0. The 1 over x squared, 1 over x, you have asymptotes, breaks in the x-axis and the y-axis. In other words, on this side, I could draw only below the x-axis, and to the left of the y-axis, this one's above the x and to the right of the y. So those are not continuous. So we'll look at continuity. So let's look at everything we can talk about when we have a polynomial equation. If we have a polynomial equation, n minus 1x, so polynomial p of x is equal to a sub n times x sub n plus a sub n minus 1 x n 1 all the way down to a1, x1, and a0. So now let's show you how to read these things. So let's say our degree was 5. Remember, the degree is n. So our polynomial would be a to the 5th, x to the 5th. N minus 1 is 5 minus 1, a to the 4th, x to the 4th. And one more, go down. A to the 3rd, x to the 3rd, a to the 2nd, x to the 2nd, a to the 1st, x to the 1st, a to the 0, x to the 0. Well, we know anything to the 0 power is 1, so it's just a to the 0. So that's what this formula means. So no matter what the degree is, we can identify the degree. Again, the degree is the largest exponent. The leading term. The leading coefficient. So in our case here, our leading term was a to the 5th, x to the 5th. It's the term with the largest exponent. The leading coefficient is the coefficient in front of the x. We're going to be able to find the zeros of polynomials by setting the polynomial equal to 0, factoring it, and solving. Once we find the zeros, we'll also then find the x-intercepts. We know the y-intercept. The y-intercept is always the constant. Constant number. It doesn't have an x behind it. That one here, a sub 0, because x is gone, x is 1. We can find the maximum minimum values. we call those the vertices. We can find the domain and the range of the function. So now we're going to start doing a lot more stuff. All the stuff, yeah, we can look at this stuff, but to finding the X-intercepts, this is the hard part. That's what chapter 4 is about. So we have to learn new ways of factoring equations. So far, what we've learned was how to factor linear equations and quadratic equations. Now we're going to do everything else. Let's look at some examples. We have a polynomial x cubed x squared minus 17x plus 15. Determine if 2 and or -5 are zeros of the polynomial. All right, so how do we do this? To find if a value x is a zero of a polynomial, just substitute every x term with that value and work out the equation. To find if x is a zero of the polynomial, just substitute that value x for every x term and work out the equation. If the equation equals 0, then x is a zero of the polynomial. If not, then it's not a zero. So here's our polynomial. There's our two values, 2 and -5. See if one or the other, or both or not, neither of them are zeros of the polynomial. X equals 2 and x equals -5. All right, so here's my polynomial, x cubed plus x squared minus 17x plus 15. P of x equals x cubed plus x squared minus 17x plus 15. So anywhere I see an x, put a 2. I like to always put my values inside parentheses, just in case. So anywhere I see an x, I put a 2 and work it out. 2 cubed is 2 times 2 times 2. 2 times 2 is 4, times 2 is 8. 2 squared, 2 times 2 is 4. Minus, it's negative times positive is negative. 17 times 2 is 34 plus 15. Eight plus 4 is 12. Twelve plus 15 is 27. Yeah, since they're not the same numbers, they're not gonna work. So the bigger number is negative. 34 minus 27 is 7. So P of 2 is 7. So 2 is not a 0.
Mr. How do you got 8 plus 4?
2 cubed is 2 times 2 times 2. 2 times 2 is 4, times 2 is 8. And 2 squared is 2 times 2, which is 4.
Oh, okay. Thank you.
Yeah, you're welcome. Yes, actually, what you just asked is a very excellent question, because the most common mistake people do is to go 2 times 3, 6. So, no, this exponent means 2 times 2 times 2, which is 8.
Yeah, because I was gonna be like 3 times 2 is 6. And then I'm confused.
Exactly. Yeah, that's the most common mistake. I'm glad you asked.
Thank you.
Now let's look at the other side. P of negative 5. So anywhere I see an x, I put a negative 5. Negative 5 cubed. Negative 5 squared. 17 times negative 5 plus 15. So negative 5 times negative 5 times negative 5. Negative is positive, times negative is negative. There's 3 negatives, so it's negative. 5 times 5 is 25. 25 times 5 is 125. So this first number is negative 125. Next one. Negative 5 times negative 5. Negative is a positive. 5 times 5 is 25. So this number is 25. Positive 25. Negative and negative is a positive. 17 times 5. 17 times 5. 5 times 7 is 35. 5 times 1 is 5, plus 3 is 8. So it's 85. Plus 15. So these 3 numbers are positive, this one's negative. So I'm going to add these two numbers together. If they equal 125, I'm in business. So positive and positive is positive. 25 plus 85. So it's 90 plus 20 is 110. Plus 15. Positive and positive is positive. 110 plus 15. So 10 plus 15 is 25. They're the same number, but different signs, so they cancel. So -5 is a 0. So by plugging in the number, we can see if it becomes a 0, then it's a 0. I mean, that's an X-intercept. And it actually, and we'll learn a little later in this chapter, it means a lot more. But for right now, it means it's a 0. So that's the first phase. Now let's find zeros of polynomials. For the first one, if I give you this equation, because this is already in factored form. This is already in factored form because remember what we did in chapter 2 is if I gave you x squared plus 6x plus 5 we took the polynomial, factored it out into this, and then we set each of these linear terms to 0, and then we solved it. We do the same thing here. We're starting from the factored form. So to find the zeros of this equation, we take each of these equations, set them equal to 0, now, very important note, this leading term here, since it's a constant, it doesn't affect anything with our zeros. But if it was a 5x, if there was an x after it, we'd have to solve that for 0 also. So it doesn't have to be inside the parentheses. If that was a 5x, then we have to have 5x equals 0. So now we solve x is 2, x is 2, x is 2, x is -1. You see, these are all the same answer. So our real answers are x is -1 and 2. We only have 2 x-intercepts. But if we looked at this equation originally, before we factored it, the leading term would be like that. So this equation, the leading term looked like this. Because we have x times x times x times x is x to the 4th. And leading coefficient is 5. So that means we can have at most 4 x-intercepts, but we ended up with 2. So what do we know about this graph? Since the leading term is positive, a is 5 and it's greater than 0. The degree is even. Remember from our table, if a is positive and we had even, all we know for sure is the end of the graphs look like this. And we know at -1, we have an intercept. And at 2, we have an intercept. And we're going to have 3 vertices. So it could, let's see, it could look like this: up, down, up, down. Or it could have crossed at -1 and done some stuff and then back up. And we don't know, but all we know is that the graph crosses at those 2 points, and since it's positive and even, that's all we know. But that's a start. We're building up on it. Actually, we can know something else. Can we rewrite this equation so it's shorter? Yes. Since we have 1, 2, 3 x minus 2s, and when we have 1 x plus 1. Whenever you have the factored form and you have these exponents are called the multiplicity of the polynomial. And the multiplicities tells us if the graph crosses or simply touches the x-axis at that point. So the multiplicity tells us a lot more than just, okay, it's just how many times this answer repeat. So the multiplicity, which are the exponents, tells us if the graph crosses or simply touches the x-axis at that point. All right. Actually, we've seen examples of this already. When we first start talking about quadratic equations, we have this graph. And cubic equations we have this graph. So P of X equals X cubed, P of X equals X squared. Like the example we just had, this is our multiplicity. This is our multiplicity. The 0, whatever's on the bottom, take it, set it equal to 0. That's our 0 value. Yep, at 0. If it's even, it bounces at that point. Even multiplicity the graph bounces off the x-axis at that point. So the multiplicity of that one is 2. The 0 is, this is the point we're looking at. So at 0, we have a multiplicity of 2. So since the multiplicity is even, at 0, the graph bounces. Same thing here. And the next one, the multiplicity is 3. The 0, whatever's under, 0 is 0. But since the multiplicity is odd, at 0, the graph crosses. So odd multiplicities the graph crosses the x-axis at that point. So that's very important because it tells us what the graph is going to do at that location. We know the 0, whatever the base is, the bottom part of that exponent, set that equal to 0, it's at 0. And if it's an odd exponent, we know the graph's going to cross at that point. If it's even, it's just going to bounce at it. So with our equation, so with our example, we know that x minus 2 happens 1, 2, 3 times, and x plus 1 happens once. And this helps us keep track of all this stuff. So what are my zeros? The first 0 is at 2. That's, I could put it there, just at 2. The multiplicity of that point is 3. The second 0 is -1. Its multiplicity is 1. So we know at +2, the graph will bounce. And at -1, the graph's going to bounce. The leading coefficient is positive, so both ends have to point the same direction. There's 1, 2, 3, 4. The degree is 4. That's how many x's we have in our equation. So both ends have to point in the same direction. They're pointing up. And so at -1 and -2, the graph bounces. So the graph looks something like this. Oops, no, it's odd. So it crosses. So it crosses. It goes down here and go down here. I'm sorry. It looks like that, not that one. Since we know it crosses. So whatever polynomial we had, we factored it out. We look at all our possible solutions, see what the multiplicities are, and that tells us what's happening at the graph at that point. Let's look at another example. So the first thing you do, term is negative. It's actually a -1. Since there's nothing there, it's a -1. X minus 1, I have 2 of those. And we have 2x plus 2's. So rearrange your terms if you have to, so they're even paired up together. So we have -1, x minus 1, there's 2 of them, x plus 2, there's 2 of those. So let's look at the zeros and multiplicities of each. The first one, set that equal to 0 and solve it. We get x equals 1. The multiplicity is 2. Since the multiplicity is even, it bounces. The second one, x plus 2 equals 0, we get x equals -2. So the 0 is -2. The multiplicity is 2, so it bounces. So we know what happens at the intercepts. They bounce. Let's see 2 more things. What is A? What is your leading coefficient? A is -1. That's less than 0, so it's a decreasing graph. And what's the degree? One, 2, 3, 4. There are 4 x's in our equation, so the degree is 4. So the degree is even. Remember the little chart we had earlier? We had even and odd. A is positive, A is negative. So the degree is even, A is, so we know that both ends point down. So this is even, and this is negative. All right, so we know what our graph is basically going to look like. It's a fourth order equation, so it's either going to look like this or like this. Since a is negative, it has to point down. The zeros are at +1. It bounces, and at -2. And it bounces. And it has to go down. So there's our graph. Or a rough sketch of what a graph might look like. Okay, so that's if it's given to you in the factored form. Now let's start factoring our own equations.
Mister, can I say one more time the graph, please?
Yes,
Thank you.
you're welcome. Yeah, so at -2 and 1, we have our zeros, and they bounce. Since the degree is 4, both ends have to point the same direction, and they point negative down. We don't know, only thing we know for sure is these ends. We don't know really what happens here. We have to plot some points. But remember, n-1, which is 4 minus 1, that's the number of vertices. We have 1, 2, 3 vertices. All right. So let's do 2 examples, 2 methods of, it's a continuation from what we did earlier. All right, so f of x equals x to the 4th plus 4x squared minus 45. So the degree the value of a the x-intercepts, the y-intercepts, the zeros, multiplicities, domain, and range. Just everything we can tell this so far with what we know. So what's our degree? 4. Since our degree is 4 and our a is whatever's in front of that, it's our leading term, is 1, then we know our graph will look something like this. We know the y-intercept is at -45. Remember, the y-intercept is always a constant. The domain of this equation, since x can be positive, negative, and 0, is everything. And the rest we have to wait to see. So let's try to factor this one. Let's first try to factor it. Because it is a trinomial, there's 3 terms. It's quadratic in form. In other words, it looks like this. Because the middle term times 2 equals the first term. The middle term, which is 1, times 2 equals the first term. And when we factor, whatever the middle term is goes inside the parentheses. So x squared. Look at the second sign. It's a minus. Since it's a minus, that means the signs have to be different. The bigger number gets a plus. So what times what is 45? When you subtract them, you get 4. So 45 times 1, but 45 minus 1 is 44. That's not right. 2 doesn't work, 3 doesn't work, 5. 9 times 5 is 45. 9 minus 5 is 4. So 9 and 5 are the numbers. 9 times 5 is 45. 9 minus 5 is 4. So the plus, 9 gets there, 5 gets that one. Now we set the equation, since we're solving for it, we take both of these, set them equal to 0. So x squared equals -9. X squared equals 5. Remember, we subtract 9 from both sides. We add 5 to both sides. Square root both sides. X equals plus or minus square root of -9. X equals plus or minus square root of 5. Square root of -9, since there's a negative inside there, that's an I. Square root of 9 is 3. And the other one is just square root of 5. We can't graph that, even though that is a solution, but it's not a real solution. So our x-intercepts are positive and negative radical 5, which is something like 2.1 or 2.05, something like that. So it's just a little bit bigger than 2. So our x-intercepts are plus minus radical 5. Radical 5, comma 0, negative radical 5, comma 0. So the x-intercepts, radical 5, comma 0, negative radical 5, comma 0. The zeros are at radical 5 and negative radical 5. The multiplicities are 1. So it's going to cross the x-axis at those points. So here's 2, here's -2, so it's just a little bit bigger. And it crosses at those points. We know the degree is 4. And A, the leading coefficient, is 1, positive. So we know that it opens up. It crosses through those endpoints. Oh, we also know that the y-intercept is -45. So somewhere it goes all the way down there. That's the only thing we know about it. Okay, so that's if we have a trinomial, see if we can factor it or use a quadratic formula if it's quadratic in form. All right, now here's another method called grouping. Grouping is used when you have 4 terms. You pair the first 2 and the second 2 equations. So here's term 1, term 2, term 3, term 4. So there's your 4 terms. So you pair them up and you factor them out from there. And then set equals 0. Let's see what that means. All right, so since we have 4 terms, we can try grouping. So the first thing we're going to do is pair the first 2. So we put parentheses around the first 2. And then pair the second 2. Now factor. What does the first pair have in common? They both have at least 2 x's. So I take out 2 x's. If I take out 2 x's here, I'm just left with x. Just x to the first. Minus 2. Because I took away those 2 x's. Now in the second pair, I need a sign. So whatever the sign of the first term is, that comes out. And they both have a 9 in common. Remember, what do I factor out? I divide. So I divided by -9, both of these. I factored out a -9. So negative becomes a positive. 9's cancel, so it's x. Positive divided by negative is negative. 18 divided by 9 is 2. So I put first 2 and second 2 in parentheses, factored out what they had in common. Again, whatever the first term sign is, that's the sign that comes out. Now, we have this term and this term. What do they have in common? They both have an x minus 2. If I remove the x minus 2's, all I have left is x squared minus 9. Because you can check to see if that's correct. X minus 2 times x squared is x squared, x minus 2. X minus 2 times negative 9, so that checks out. We still have a quadratic equation here. So since we only have 2 terms, I mean, we could, since we have 2 terms, we could take this equation, set it equal to 0, and work it out. Square root both sides, you get plus or minus 3. But we discussed we can also factor this one out because 9 is made up of 3 squared. So we have the difference of 2 squares, which means I take the numbers that are inside the parentheses, x and 3, that x and that 3, and one sign has a positive, one sign has a negative. Now we solve. X minus 2 equals 0, x plus 3 equals 0, x minus 3 equals 0. So the answer is positive 2, negative 3, positive 3. Yeah, these two, again, we figured it out that way. So those are our solutions, our zeros. The multiplicities. We have a 2, we have a negative 3, and we have a positive 3. The multiplicities are 1, 1, and 1. So it crosses, crosses, and crosses at those points. So positive 2, positive 3, and at negative 3. We know the degree is 3. That's the highest exponent. And the y-intercept is positive 18. So we know it crosses at positive 18. The degree is 3. So and the leading term a is 1, so it's positive. So the graph will look something like this. It's a cubic equation. So we know this side has to go down. This side has to go up. So it'll look something like this. Let me see, let me find another example here for that type. No, 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 no. Are there any questions so far while I'm looking?
Nope.
No questions? Okay. Okay, then I'm going to ask you a few questions. 2 questions here. Here's a polynomial. 2x cubed minus 3x squared plus x plus 6. Tell me which one of these are zeros. And let's see. And then tell me the zeros, multiplicities, and try to lightly sketch this graph. All right, so here are your 2 exit questions. So remember, just plug those in there and see what happens. So the first one's a no. Is 27. Okay, so out of all those, the third one works. It gave us a 0 at the end. So once the answer becomes a 0, we know that x equals 1 is a 0, is a solution, is an X-intercept. All right, let's look at this one. Since we have 4 terms, put the first 2 in parentheses and the last 2 in parentheses. What can we factor out of here? They both have 2 x's. So if I divide each of these by x squared, that becomes just single x, and that just becomes a 3. Only thing these have in common is a -1. So it just changes signs. They're both negative, so I take out the negative. That changes their signs. They both have an x plus 3. So once I take out x plus 3s, whatever I have left are the coefficients. X squared minus 1. Again, this last one, if you wanted to, you can just go ahead and solve it. So x squared equals 1, square root both sides, x equals plus or minus 1. So those are these 2 answers. Or if you wanted to look at that, we know that this is the same thing as 1 squared. So it's a difference of 2 squared. So it's x plus 1, x minus 1. Set each of these equal to 0. You get -3, -1, +1. Yeah, we know what 2 of them already. The zeros are -3, -1, +1, and their multiplicities are all 1. So they cross the x-axis, they cross the x-axis, they cross the x-axis. The degree of the equation is 3. We have 1, 2, 3 3s, 3 x's. The leading term is 1, so it's greater than 0. So -3, -1, 1, 2, 3. We have zeros at -3, -1, and 1. We have a y-intercept at -3. That's the y-intercept. So since the degree is 3 and it's positive, we know that this end goes down, this end goes up. So that's the graph. All right, I hope that helped everybody. So yeah, this is just the beginning, because now we're going to start looking at bigger, larger, harder equations, and we're going to start learning new methods to solve these. So this is only the first step. You have to understand this first.
For the multiplicity, so it's gonna be a 1.
Well, no,
On
not
the-
always, not always. It just happens in this case it was. Because, I mean, we could get equations. What if I gave you this equation? Let me see. So if I give you x cubed plus 3x squared minus 4x minus 12. Let's look at this one. Hold it. 9. Not that this one. That gives us 3 separate ones. So x squared, 3x squared minus 9 and negative 27. Let's look at that one. So x cubed plus 3x squared minus 9x minus 27. So set parentheses around the first two and the second two. We can take out x squared out of the first one. X plus 3. We take out the first sign, take a negative. 9 and 27, they both have a 9 in common. So remember, whatever I factor out, I divide to see what goes inside here. Negative and negative is positive. 9's cancel, so it's just x. Negative, negative cancel, so it's positive. 27 divided by 9 is 3. They both have an x plus 3. So whatever's in front of those go inside the second parenthesis. Nine is made up of 3 times 3, so this is the same as 3 squared. So it's a difference of 2 squares. So it's x plus 3, x minus 3. Now we have a different multiplicity. This one's going to be negative 3. The multiplicity is 2. This one's positive 3. The multiplicity is 1. So this one bounces, this one crosses. And the y-intercept's at negative 27. So at negative 3, the multiplicity is 2. The degree is 3. A is 1, so it's positive. So our graph goes down there and up there. So at negative 3, it bounces. And then crosses at positive 3. So there's that one. So it just always depends on what the equation is. All right, yeah, so I mean, on Wednesday, what we're going to do is we'll work step by step the homework problems. And so we can work it through so we see exactly how it works. All right. Anybody have any questions?
Thank you.
You're very welcome. Thanks for showing up today, everybody.
Bye, mister. Thank you.
You're very welcome. Bye.